Good afternoon, everybody, and welcome to the LCANZ Autumn Webinar Series, the fourth webinar in our series, in fact. We've got recordings available for the first three webinars that we've already shared. Please check out the LCANZ website to find those. And we still have 4 more webinars coming up after today. So again, please check out the LCANZ website, check us out on social media, and go register for those because we've got some really cool stuff still coming up. Also, as a reminder, and added inducement, we are running a bit of a competition this year to win a year's LCANZ membership. So starting for the next financial year. If you're a student or an individual member, you can win your own membership for the next year, and corporate members can gift membership to an SME to increase the span of membership of LCANZ and get more people on board. So to be in for a chance to win, please register, attend the sessions, and there will be a short quiz at the end of all the sessions about what you've heard. So pay attention. Troy Coyle is CEO of HERA, long time, in fact, I think founding member of LCANZ, and is here to talk to us today about zero carbon steel. And Troy, I will hand over to you with no more ado.
The reason why we wanted to do this is because the world's largest material industry is actually steel. It generates a turnover of $1 trillion and is 10 times larger than the aluminium industry, 7.5 times larger than the copper industry, and 4 times that of the cement industry. It also plays a prominent role in our daily lives and is critical to national infrastructure. So it's a key part of our bridges, our rail system, our road system, our commercial and industrial buildings, and even our residential homes. But that demand for steel in all of those applications there is actually anticipated to increase by more than 1/3 through to 2050. So if we are going to achieve a global transition to a clean energy economy and meet our carbon emission targets, steel actually needs to improve its carbon performance, and we need to acknowledge the role of steel in providing that solution. So steel plays a role in the infrastructure also required to transition to that low carbon economy. So it's in our wind systems, it's in our hydroelectric systems, it's in our wave energy systems, geothermal, and even our photovoltaic systems. However, there's no doubt that steel is a large emitter of carbon. It's emitting 2.6 gigatons of carbon dioxide annually, and that's worth around 7% of the global total from the energy system and more than the emissions from all road freight. So if we're going to meet our target, we have to really look at how we're going to transition steelmaking to become net zero. And that is not an easy feat. And the reason why steel is considered hard to abate is actually because of the chemical equations involved in steelmaking. So there is a misconception that the carbon is coming from the burning of coal to create fuel or heat, but it's actually part of the chemistry involved in transferring iron into steel. So basically we're taking iron oxides, adding the coal, and the byproduct is CO2 by taking that oxygen off the iron, which is then converted into steel. So if we look at a generalized steelmaking process, basically all steelmaking in the world would be made up of either of these 2 methods or a combination of both. And the first method at the top there is what's referred to as a mini mill or electric arc furnace process. That takes scrap, so basically recycled steel, and converts that into new steel product. That's a really efficient process. For every 1 ton of steel, only 0.3 tons of CO2 scope 2 emissions are created, and only 0.04 tons of CO2 scope 1 emissions are created. About 30% of steelmaking is using that method globally. In terms of the more prevalent method, it's the one that I referred to earlier, where we're actually taking iron or adding in the coal, converting it to more pure forms of iron, and then converting it into steel. And that process is quite carbon intensive. For scope 1 and 2 emissions, for every 1 ton of steel, there are 1.4 to 2.2 tons of CO2 created. Unfortunately, no commercially viable alternative to coal as the reductant is in existence, but that doesn't mean the industry is doing nothing. And there is a lot of research that's happening overseas, particularly in Sweden, around using hydrogen as the alternative reductant. So in that equation, the byproduct would be water. That has been going well with some really promising results. However, at this point in time, it's only available for high-end niche markets and low volume. So for example, at the moment, it's being used for aspects of the automotive industry and isn't really accessible for bulk production of steel. So that's the holy grail. And we can't really wait for that to happen. We need to be carbon zero now. And that's the challenge that HERA wanted to address. So there is a lot of work happening around that holy grail of the hydrogen reductant, even in New Zealand, through Chris Bumby's work at Victoria University. But the problem is that we need to get those reductions a lot earlier than the anticipated 2040, that technology is supposed to be more widely available. And the steel industry has got a few initiatives in terms of improving processes to reduce carbon emissions. But in terms of the steel that's being produced, we really need an alternative approach in the short term, recognizing that's not ideal and that carbon reduction should be the ultimate goal. And that really is through carbon offsetting. So that's the program that we have been working on. It is basically a calculator that then determines the required offsetting. We're partnering with ECOS for those offsets. So we've deliberately chosen those offsets to be based on native forests because we want to get the other additional biodiversity and other living standards framework benefits from the social and human capital buckets. And the outcome for the user of the calculator is that they are able to provide zero carbon certified steel. And so that process would be either a fabricator would use that to offset product that has already been chosen for a construction, or it might be that a fabricator wants to offer two options. And the idea of the program is to start to get a awareness and create a market for specifying zero carbon steel. And so they may offer a zero carbon steel option as well as a regular steel option, and that would bring that to the attention of the project owner that this option does exist. It's the first of its kind in the world, and one of the reasons why it's the first of its kind is that it covers a broad range of steel products. So it includes roofing and cladding products, includes light gauge steel framing, the heavy structural steel that would be used for major infrastructure. It includes stainless steel, and it also includes rebar. And it also includes some minor components, for example, bolts that would be used in the bigger structural elements. In terms of LCA, it's a cradle to installation, so modules A1 to A5 program. The primary element of it in terms of the carbon production is the actual making of the steel, so the steel production. In our program rules, LCA data is required for the production component, and that has to be through an EPD or industry LCA study. We've also included transport distances and modes, and that comes from DOE data. We've also included fabrication based on data from New Zealand fabricators. So this is data that we couldn't find independently, and we had to go out and do a study to determine what that carbon cost would be, as well as installation. And that's not for all products, but where products are going to use additional intensity. So for example, for a smaller roof, it's not typical to use a crane, but above 200 meters squared, it becomes more common to start to use a crane. So that's part of the calculator as well. So in terms of the LCA and EPD data, an EPD published under a recognised program and based on an appropriate product category rule is acceptable, as is a life cycle assessment based on an appropriate PCR, if available, or an EPD for a similar product where both are produced in the Australasian market. The other data is industry sector EPDs. So where the EPD states the variability, we will take the upper end of that stated variability for the global warming potential impact. and we add it to account for uncertainty. And where the variability isn't stated, we add in a 10% global warming impact to account for the uncertainty. And we think that's at the upper end of that uncertainty, and so is considered to be conservative. And it's obviously providing an incentive for suppliers to provide the more reliable data. In terms of industry average LCA data, that must be published by a reputable industry body, for example, World Steel or the International Stainless Steel Forum, and an additional 15% global warming impact must be added to account for the uncertainty. And again, that's considered conservative and an incentive for suppliers to start developing the right EPD and LCA data to get rid of that global warming impact factor. So it's a pretty simple system. We've got our product guidelines, or the program instructions. So that basically outlines what products can go into the calculator based on what data. We've got the actual data around production that goes into the calculator. We then add in the fabrication emissions, the transportation emissions, and the installation emissions. And the sum of those derives the total footprint for the product. As I said, we don't see this as a panacea for, the carbon issues associated with steel. And there are other areas that HERA, as an independent research association, is working on to fill in some gaps. Another exciting project that will look at increasing the reuse of steel is the development of Australasia's first material passport. And that passport, it will basically enable reuse of structural steel in the first instance, but hopefully we will take those learnings and apply it to all building materials more broadly. And the way that I think of the material passport, because it's not commonly known or understood in New Zealand, is that it's basically making a piece of infrastructure or building a bank of materials so that you can withdraw those materials at end of life. And it's particularly easy for steel because basically with bolted structural steel, you can just take out the bolts. And if you know what the quality and life experience of that piece of steel has been, you can readily reuse it. And also we're looking at extending lifetimes. So the building code at the moment for structural steel requires a 50-year lifetime. What could we do at the specification stage and in terms of what we know around durability and performance to actually double that lifetime to be 100 years and start to reduce the carbon in that way?
Fabulous. Thank you, Troy. That was fantastic. Really good talk through of quite a complicated topic. I'd just like to encourage everyone, please don't forget, use the question and answer panel to put your questions forward, and I might jump in the interim. Obviously, this has been driven by the sector, but how is the uptake working with the sector? What's the process to get people on board?
Mm-hmm. So I should say that we're planning to launch this in April. We're just working on our how to support documentation at the moment. So the process will be that HERA will put it onto our website and we make it freely available. The only criteria or restriction is that we don't want it to be used as a calculator. We want it to be used as an offset scheme, so a zero carbon scheme. So there has to be a commitment that it's going to be used in that way, that ultimately we're going to be offering a zero carbon product by using the calculator. We think that a large part of the projects are quite complex, so there'll be a two-step or two-option process. For the simpler ones, we can do that all online using the program. For more complicated ones, we will liaise directly with ECOS and determine the carbon associated with the range of products that might be involved in that particular project.
Thank you. I don't think I'm giving away any industry secrets to say that we were involved in the development of it. So having seen, we worked through a few test projects, didn't we, with for the different sectors, and yeah, the the complexity from a simple single dwelling roof to some of the structural stuff was suddenly massive change in volume and complexity. So it makes sense to have the support from ECOS, but also more verification, because as it's getting bigger, it definitely needs that more scrutiny over what's happening.
Yeah, definitely. And we want to have that independence too. HERA is basically the project initiator, but we're pretty hands-off in terms of how the program rules are applied and what products go in. So if a producer wanted to add in a new product, they would need to notify us, and we would basically outsource to a provider like ThinkStep to determine whether it meets the product rules. And sorry, I didn't answer the other part of your question earlier, which was what's the interest looking like? And I would say that I am getting almost daily inquiries about the program. Unfortunately, we thought we were going to release it last year, and it's taken a bit longer, but that has meant that we've had a bit of time to create a bit of awareness and interest as well.
I'll be waiting with bated breath for when it launches. Awesome, thank you. So I've got some questions rolling in from Stuart. So the embodied carbon is effectively used up over the life of the product, and the longer it lasts, the lower the carbon per annum. So if steel is effectively recyclable indefinitely, the true carbon per annum is minimal.
Correct. So if we can extend lifetimes, obviously the carbon is amortized over a longer period of time, so that has a carbon benefit. And we have done a report around recycling of steel, which we used ThinkStep to develop for us. And in New Zealand, it is unfortunate that our steel is exported overseas for recycling. However, there's still a significant carbon saving from doing that. So for the building and construction component of that scrap, it was around almost 1,500 tonnes CO2 equivalent emission savings per tonne of scrap. So there is a significant benefit still of that recycling, although it's done overseas. And I think the obvious question that we always get asked is, why don't we use that first method, the electric arc furnace? And that's a really important link to the recycling rates, because the demand for steel globally is so high that we're not at all able to meet the demand from the recycling of existing steel at end of life. So yes, the recycling is important, but in terms of specifying recycled material, it doesn't really help overall, because there's just too much demand for new steel than we can meet with recycling of steel.
Yeah, and especially with the growth that the industry is expecting to see coming up. That's, yeah, very important point. Wonderful. So a question from Straussy with a comment that was really great. She'd like to understand more about the alternate reduction technique using hydrogen. You mentioned it's being used in place of coal, but only in small quantities. But coal as a reducing agent is used in blast furnaces, which are not really switched off, they're always running. So why is it then used only for higher end products, especially if the process works and not bulk steel?
The project that has advanced that technology the most is a really interesting project out of Sweden, which is a collaboration which I think is really exciting between one of Europe's largest energy providers, the actual steelmaking company, and also the raw materials supplier. And so basically it's encompassed that whole supply chain to work together. And that has received a lot of investment. And just recently, last year, they made their first steel using that and basically proved the concept. But even they say, because SSAB do have blast furnaces, and so they anticipate that they won't be able to convert over to full steel production using that method until 2040. So there's still a lot of work that needs to be done in scaling up that technology. And at the moment, it's very expensive steel and also very high quality steel, which that metallurgy isn't usually used in building and construction.
Yeah, it's a good point. I think it's also important to remember that most hydrogen produced at the moment is probably produced using electricity grids that are not as clean as those in New Zealand. And quite often it's produced from something like natural gas. So if we can get to a place where we've got green hydrogen, where it's produced from water and using renewable electricity, we get double the benefits. Because, I mean, it certainly would help steel anyway, moving from coal to even the dirtiest of hydrogens. But yeah, there's room to improve that as well.
Yes,
Cool.
and I think also for us, because New Zealand Steel is owned by the Australian parent BlueScope Steel, and BlueScope Steel has announced a relationship with New South Wales investment into a hydrogen production facility, which will be basically co-located with them. It will be located very geographically close. So it'll be exciting to see what happens there in terms of basically a close supply of hydrogen to the steelmaking facility.
Yeah, very exciting stuff coming up. Wonderful. So another question then from Aaron. At today's rates, what's the rough cost, in terms of percentages, to offset carbon for the two types of steel manufacturer for a typical commercial project in New Zealand?
So I'm not sure about the two types of manufacturer, but basically we have done some cost calculations, and we believe it to be around a 10%, between a 5 to 15%, but typically more around the 9 to 10% increase in cost. So I'm mainly working structural steel, so that's the really heavy steel where it's much more tonnages, but also I guess more carbon intensive per dollar value of that product. Because, for example, roofing and cladding is a lot less steel, but it's a higher value per ton product. So yeah, at that heavy end, it's around about that 10%, which if you looked at, for example, multi-story construction, I know there's a lot of conversations around using timber, and I'm not advocating steel is better than timber. I think there's a place for both, but there is a significant cost difference between the construction of bulk timber versus multi-story structural steel, to the advantage of steel, between 50 to 90%. And so that 10% difference, I think, makes it really interesting around the combination of affordability and sustainability.
Yeah, absolutely. And as you said, helps to also focus on that, why we need to reduce. Staying is important. Thank you. I don't know who sent this in. We have an anonymous question. So when calculating A1 to A3 embodied carbon on structural projects, I've noticed a big variation in the embodied carbon of steel based on where it's sourced using brands data. So for example, BlueScope steel from Australia is around 2.75 kilograms CO2e per kg, while steel imported from Europe generally has much lower values of about 1.13. Why is the embodied carbon so much lower in Europe? It insinuates it could be environmentally beneficial to import steel from across the globe rather than using steel local to Australasia. Wash your mouth out, whoever you are. We don't want to hear that.
Yeah, I guess, yeah, it's a complex decision making, isn't it? Because there are environmental issues associated with, offshore manufacture and transport. But I think that the key reason why you would see significant variations in CO2 emissions per tonne of steel would be around what method is being used to produce that steel. So if it's that first method, that electric arc furnace method, that's likely to be, well, it will be significantly lower than using a blast furnace or any of those second methods.
Yeah, agreed. And also, to whoever sent that in, not to forget that you need to include the transport of the steel from Europe, which it might not fully make up the difference, but it would make a significant impact, especially when you're bringing it that far, which is an important part of what the calculator and the rules do as well, to make sure that we are comparing fairly across products. Troy, thank you so much again. That was really interesting, very useful, and I think some good questions and discussion. Thank you also to everybody who joined today. Don't forget, we've got more webinars coming up, so please do register, and don't forget we've got a competition. So hope to see you all. We do have a break now until the 13th of April. So there's a couple of weeks where you get your lunch times back on Wednesdays. But we'll see you on the 13th before another break for Easter and the school holidays. So next up is Firth's Embodied Carbon Calculator. Look forward to seeing you then.